If you want a picture of the universe, you think of it as a sponge, so that the material of the sponge is where the galaxies are, and the holes are where the voids in the distribution are. Try this experiment at night. When you have your bath, take a piece of thread, and you will find you can put it all the way through the sponge and take it out the other side. Don't blame me if you do it. But what that means is, it means that it's a multiply connected system where the galaxies are all connected and the holes are all connected. And that gives you very important constraints on how the galaxies came about. So the dark matter is certainly present in the galaxies and the clusters and the larger structures, but its nature is not established. But watch this space closely. Things are about to happen. For example, direct detections of dark matter particles are now reaching sensitivity that will not be a surprise if they happen soon. And some of that work is being done, excellent work being done here in Edinburgh. And secondly, the experiments at CERN, the Large Hadron Collider, may detect the lightest supersymmetric particle, which is one of the strong candidates for the dark matter. So there are a lot of very exciting things to be happening in this area of dark matter. But the reason I call it a hard problem, it's hard, but it's doable. Right? And I expect something will happen within the next 2 to 10 years, perhaps even more recently. Point 3, the dark energy. Well, this all comes from cosmological studies started by Edwin Hubble in 1929. And he observed that the greater the speed galaxy is away from us, the greater speed it moves away from us. And this is the technical picture of what the data look like. Here we see velocity up the vertical axis, distance along this axis, and correlations don't come any better than that in astronomy, I can assure you. So the velocity is proportional to distance. The other thing we need is the large-scale distribution of matter radiation in the universe. And this nowadays comes from the COBE observations of the microwave background radiation. And this is one of the most spectacular pictures in the whole of astronomy. This is utterly an incredible picture which, again, simplifies the whole construction of cosmological models. There's the whole sky. The sky in the millimeter wave band is exactly the same in all directions, with a remarkable precision. In fact, if we go down a factor of 1,000, we begin to see the plane of our galaxy coming back as well as our motion through it. And we have to go down to one factor of 100,000 to begin to see structure which is of cosmological origin. There's the plane of the galaxy. We throw that away because we're cosmologists this evening. But these little ripples at high and low latitude, these are the fingerprints of the structures from which the large-scale structure formed. That's very, very important. Now, let me show you a little simulation which is great fun. If we put together the Hubble law with the isotropy of the universe, then we can show that the universe as a whole must be expanding uniformly. Let's see if we can bring up this little simulation. Now, this is a nice little simulation that Paul Alexander and I put together. And what we've done is to borrow some galaxies from the Hubble Deep Field. We just took them off the Hubble Deep Field and stuck them on a piece of paper. And we said, now let's suppose that these all expand uniformly away from each other. What do we expect to see? Well, let's just see what happens if we run the program. There you see the galaxies all moving apart uniformly. It's as if you had lots of dots on a rubber sheet, say, and you simply pulled it uniformly. You would see these points all moving away one from the other. Well, what's fun is if you reset the program and we select a galaxy at random and 2 other galaxies at random, all at random. That's very, very important. So let's do that. So here we go. We'll choose our galaxy at random and draw arrows to 2 other galaxies, which you see is what I've done there. Now let's run the simulation again, and you can see what happens. We've run the simulation, and you can see the motion of these galaxies relative to their original position. And if we stop it there, you'll see the beautiful result that since that all happens at the same time, the one which is further away must be proportionately moving faster than the one that was closer to begin with. That's Hubble's law. It's telling us in the same time interval, the ones which are further away have got to move further to make sure we keep the universe uniform. So in lectures like this, I'm often asked, does that mean that we are at the centre of the universe? And the answer is yes. We are at the centre of the universe. But so is everybody else. Because, remember, we chose the galaxy at random. And therefore everybody sees the same expanding universe. And that's such a glorious simplification of the sums. We wouldn't be able to do cosmology without that wonderful, wonderful discovery. So, in the standard models of the universe, we can simulate them by an expanding sphere, which is expanding at speed v, and gravity is pulling it back. And that turns out to be a very good model for the universe. Now, back in 1917, soon after Einstein had discovered general relativity, he actually created the first fully self-consistent scientific model of the universe. But of course, this is before 1929, when the expansion of the universe was known. So Einstein had to produce a static universe. So what he did was to do the following. He said, okay, gravity will make the whole system collapse, so let me put in another opposite term which will prevent it collapsing in the opposite direction. And this was the famous lambda term, the cosmological constant, which he introduced in 1917. Now, if you don't like mathematics, just close your eyes for 1 second, right? This is the expression for the expanding universe, which, again, all of the scientists in the audience can derive in their sleep. True? Yes. It's telling us two things. It's telling us that the universe is suffering two forces. One is the deceleration due to gravity, with the minus sign here, and the other is the lambda term, which Einstein put in, which is, you can see it's the repulsive effect of a vacuum. Because suppose there was no matter, no density, that term would disappear, and then you find that test particles would move apart under the influence of nothing. So it's a very strange sort of force which had no classical interpretation. But nowadays, we know that there are zero-point energies in all vacuum fields, and so we now identify that term with the dark energy. That's the thing which, again, is exercising everyone's great interest. So now that we've got a theory of where it comes from, you can work out what the value of lambda should be. And that's not too difficult to sum. There's only one wee problem, is that when you work out the theoretical estimates of the energy density of vacuum fields, they overestimate lambda by a factor of 10 to the 120. That's 1 and 120 zero. Now, that's a wee problem, right? Big problem, right? Because every theorist and his dog have been working on this problem, trying to find out how you can solve it, and there's no solution yet satisfactorily found for it. But that doesn't matter. We should test and find out whether the stuff is there or not. So how can we then reconcile the remarkable smoothness of the background radiation with the structure that we see in the universe now? Well, the best thing to do is simply look at a simulation. And this is a simulation of how the dark matter behaves in the universe. We'll go back to another of these simulations and run it again. Here's, again, just a particular very simple spectrum being put in, and this is showing the formation of structure on the large scale simply under the influence of gravity. And see, what gravity is doing is pulling together all of this dark matter, and this is all happening in the dark matter, pulling it into these long stringy structures and forming very naturally these walls and the voids in the large scale distribution of galaxies. It's really a tremendous achievement. So, this has been done in great detail. Again, the people in Edinburgh here have been deeply involved in making this work. Now, one of the great tests of this picture is that there should be structure on the microwave background radiation associated with the very earliest formations of these structures. In other words, looking back to when the universe was only 370,000 years old, which is this surface, that's where the microwave background originated. And you can then work out rather clever sums to work out how much structure there should be on different angular scales. And this has been beautifully done by the WMAP experiment. So here's another version of the Kobe map I showed before. What WMAP has done is to produce this sort of picture. And you can see it looks similar, but we've now got lots of resolution on it, and you will see lots and lots of hot spots and lots and lots of dark patches as well. It certainly doesn't look like a random distribution. And one of the great miracles is if you run this through the theory, you will find here the points are showing the observations, and the red line is showing the expectations of theory of this standard picture that I've been describing. It is absolutely miraculous. The theory and the observations are tying together absolutely beautifully.